Hello, I'm very happy to welcome you all today, and I'm very happy that we have so many students and that we have so many representatives of our college. Thank you very much. We have 3 delegates from Aramco who are all specializing in the field of quantum computation and quantum security. And I would like to first introduce all the 3 of them, and then I would like to invite the speaker on stage. So Engineer Abdulelah Alghamdi will be our speaker today. He has a bachelor degree from King Faisal University in computer science, and then he earned a master degree from Georgia Tech in information cybersecurity. So we are already impressed, all of us. And he has been working with Aramco since 2013. That is 11 years. You were not in the university yet, right, with us. And then we have 2 more gentlemen. We have Engineer Abdullah Alisa, and he's the head of cryptography solutions in Aramco and the cybersecurity chair representative with local universities. So it is Engineer Abdullah Alisa that we usually talk with, and we are looking forward to a very strong communication and collaboration between Aramco and our college. Thank you very much for joining. And engineer, here comes the surprise. And Engineer Abdullah Alisa, same name.
Because the father name is different. So.
The father name is different, good. So also Engineer Abdullah Alisa, who is the quantum computing lead in Aramco, and who specializes very narrowly on quantum computation. Please welcome all the 3 invitees that have joined us today. Thank you very much for the effort that you put into this. So to present ourselves to you, the students that are here today are all senior students, 3 sections that are taking the quantum security and quantum computation course in our college. It is offered for the first time, and we are very happy to announce that we, together with KFUPM, we couldn't be a bit early, but we started together the first. So please give a clap to our college that we did open this course together with others, but for the first time. Thank you very much. I also would like to appreciate the students. We had project presentations today for 1 section, and we have 2 more sections tomorrow and the day after. And I already have the impression that there was a lot of enthusiasm from the students, and not only enthusiasm, but very broad coverage of the purpose. We had one which is a review paper. We had one which is for the general public. We had one which works, which is a new page on Wikipedia, so that Arabic speakers can connect to this field. I think there is, a lot of things for us to do. I want to share this with our university colleagues, is that one of the challenges that the students had were to find Arabic words for the quantum specific concepts. And I am very excited to be at this moment in history here, where even the vocabulary is forming under our eyes. We also have many more projects that we are looking forward to see tomorrow. Some are hopefully published in as the form of research, and some are published for the general public, and some are for us to enjoy. So thank you very much, students, and I hope that our invitees and also our college appreciates you to the full. I also wish that you have very good jobs once you finish this. So without further ado, I would like to invite our speaker today to the podium, which is Engineer Abdulelah Alghamdi. Thank you. So thank you very much. We are looking forward to see many new things that we know or we don't know or we have known. And we would like our Dean, Dr. Abdullah, to please come to the podium and hand over the recognition for you. Thank you very much.
بسم الله والصلاة والسلام على رسول الله سيدنا محمد وعلى آله وصحبه أجمعين. Would like to welcome you all today and would like to thanks the Aramco team, Mr. Abdullah Al-Isa, the President of Saudi Aramco Cybersecurity Chair, also Mr. Abdulelah Alghamdi, our speaker for today, and also Mr. Abdullah Al-Isa, the lead in quantum cryptography. I believe this is the first time we open this course, quantum computing and quantum cryptography. Although that Dr. and I have proposed this course a couple of years ago, maybe 4 years. However, the students are, I can say that they are a bit afraid of this course. They think that there's a lot of math, I believe, behind it. There is maybe a bit of struggle, but I believe we need specialized people in this domain. This domain is very important for the future. And I believe there is a lot of discussion before opening this course. The student was a bit not comfortable studying this course. Hopefully now they are more enjoying and more appreciating this domain. The college, actually, we have a strong partnership with Saudi Aramco. And Aramco emphasized the importance of quantum cryptography and quantum computing. And I believe for them joining us today is one of the highlights how this is important and showing what the Aramco vision in quantum cryptography and quantum computing. And I believe you are the first batch will graduate from the college with this capability. And hopefully you will be one of the leaders in quantum cryptography, inshallah, in the future. And Aramco also will give you some directions, what the things that they are focusing more, what I believe they have the result, big investment in Saudi Aramco in quantum field. So we'd like you to also be the workforce that will help to contribute to this domain. I know that there's 2 sessions today and also there's next week. So I hope that you will enjoy it and you will benefit from that one. And again, special thanks to Dr. Naya for also organizing, with Dr. Adima, organizing this event. Thanks for all who attended. And we looking forward to enrich the quantum cryptography skills, research. I know that Dr. Naya have started quantum research with our students since 2017. We have a good publication in top journals with the students, and we are very proud of that one. But I believe after this course, we'll go more faster and with a larger capabilities, inshallah. So thank you all, and a small token of appreciation to Mr. Abdullah.
Assalamu alaikum wa rahmatullahi wa barakatuh, and good morning, everyone. Thank you, Dr. Naya, for the introduction and for organizing these sessions. I'm thrilled to present to you today an interesting topic about quantum. The subject will be divided, as Dr. mentioned, into 2 sessions, where the first session, which is today, will be focusing on the quantum technology. We'll explore the principles of quantum mechanics and how they are shaping the future of this technology. The second session will be focusing mainly on post-quantum cryptography subject. It will give you an overview about the potential cybersecurity threats that are associated with quantum computing. It will also highlight the technologies that are available today to protect against these future attacks. Simply how to become a quantum safe. Without further ado, let's start our presentation. In today's session, we will have an overview about quantum technology. Then we will move to the quantum technology principles. This will be followed by talking a little bit about the quantum technology domain. Then we will have some knowledge about the advantages of quantum computing. After that, I'll give you a high-level overview and comparison between the quantum computers and classical computers, which will be followed by giving you a vision about the most popular quantum computing types. And I'll conclude my presentation by giving you or talking a little bit about the quantum computers in the era of AI and ML. And we'll show you the relationship between these two technologies. So what's quantum technology? Quantum technology is an emerging technology that's using the principles of quantum mechanics, which governs how subatomic particles interact to advance the technological processes. Quantum technology works by leveraging the advantages of two fundamental quantum principles, which are called superposition and entanglement. We'll talk about these principles in details in the coming slide. Quantum technology field covers three main domains, which are the quantum computing, quantum communication, and quantum sensing. Moving on to the quantum principles, as mentioned, there are two fundamental principles, superposition and entanglement. But before we jump to these principles, let's understand first of all the quantum bits or qubit, which is the fundamental unit in information quantum computers that is corresponding to the bits or binary digit in the classical or conventional computers. Qubits are storing information similar to the bits in classical computers, but in a different way. This is because of the quantum mechanics. Unlike bits in the conventional computers, which can represent only one state at a time, for example, 0 or 1, the qubits can hold multiple states at the same time. This takes us to the two concepts of quantum principles, starting with the superposition. So what does superposition mean? Superposition means multiple possibilities, which is a property of quantum system to exist in multiple states as long as it's not measured. For example, a qubit can exhibit two quantum states, 0 and 1, at the same time, as long as it's not measured. Whenever the value or the qubit is measured, then this superposition state collapses, and the ultimate value of the qubit becomes either 0 or 1. Now moving on to the other principle, which is entanglement. Entanglement is a quantum physical phenomena in which the quantum states of two particles or two qubits, example, the photons, electrons, are entangled together. They are linked, regardless of their physical separation. So if we have two qubits that are entangled, if the first qubit is in the right side of the universe and the second qubit is in the left side of the universe, if they are entangled, then there will be a relationship between them. To explain it further, there is a quantum property that's called spin. So if we have two entangled qubits and we have this spin, and we know that the first qubit is holding the upper side of the spin, then without measuring the second qubit, we will know that it's in the downside of the spin. If we changed the value of the first spin to be in the downside, then the second qubit will move to the upper side even without measuring it. This is because of the entanglement property. Any changes to the first entangled qubit will affect the second one. Now let's get back to the quantum domains mentioned earlier and demonstrate them in further details. So the first domain is called quantum computing domain, which is an emerging technology that's combining computer sciences, physics, and mathematics that is used to solve complex problems that are considered impossible, cannot be solved by the traditional computers, or they can be solved, but they're taking a very long time. Quantum computing fields includes the hardware development, hardware build, research, and the application development in addition to the simulations. Researchers believe that quantum computers will not replace the conventional computers. They will rather work together. They will complement each other because there are some tasks that are only possible to be solved by quantum computers, other tasks that are only being solved by the classical computers. The second quantum technology domain is called quantum communication. Quantum communication, as you can see in the slides, is a technology that can create a secure tamper-proof communication network channels. These channels can be used to transfer information between endpoints securely. Why these communication channels are secured? This is because given the fact that they are using photons in a superposition state. This is used when transferring the data. Whenever someone tries to attempt to interrupt or eavesdrop these photons, then the superposition state will be collapsed. This means that the transition will be aborted. And this is why the quantum communication technology is considered secured and unbreakable. One of the technologies that are depending on quantum communication is called QKD, or quantum key distribution. This will be explained further in the next session, inshallah, next week, because it's part of the quantum computing security. Moving on, the last domain or third domain of the quantum technology is called quantum sensing, which is an advanced generation of sensors that are built from quantum systems with enhanced accuracy in measuring and detecting different physical properties. This includes the variations in motions, temperature, electric fields, magnetic fields with extreme sensitivity because of the nature of subatomic particles in quantum mechanics. Quantum sensing could improve the capabilities of the existing technologies. We're talking here about the aircrafts, automobile, weather forecasting, as well as healthcare and medicine development. So all of these domains, the quantum computing, quantum communication, as well as quantum sensing, are sharing the same quantum principles, which were explained earlier, the superposition and entanglement. Now, what are the advantages of quantum computing? First of all, we need to know that the existing quantum computers haven't reached to a computational power level that make them better or allow them to perform tasks better than the classical computers or conventional computers. They also haven't reached to a level where they could cause serious cybersecurity threats. However, leading organizations such as IBM, Google, Pascal, Intel, and other big organizations are in the race to develop enterprise quantum computers. Quantum computers have the potential to revolutionize various industries and domains. So quantum computers ultimately will provide extremely fast computational power that is increased exponentially. They will bring highly secured communication channels, and they will leverage its capabilities to improve the AI and ML technologies. Now let's have a high-level comparison between the classical computing and quantum computing. The comparison will be depending on four factors: the representation state, the way of processing the information, computational power, as well as the operation environment and the error rate. So first we start with the state representation. As you can see, in classical computing, units are measured in bits, and they can represent 0 or 1. While in the quantum computing, units are called qubits, and they could be 0 and 1 at the same time. This is because of the superposition state. In terms of information processing, information are processed sequentially in the classical computer, and they are processed parallelly in the quantum computers. For example, if we have an application in classical computer that has to execute 100 tasks, then it's executing these tasks one by one. While in quantum computers, these tasks will be executed all at the same time. This is because of the entanglement process that we explained earlier. In terms of the computational performance, in classical computing, the power is increasing linearly with the number of transistors or CPUs. While in quantum computers, it's increased exponentially with the number of qubits or QPU. For example, if we have a classical computer with a CPU that has 4 cores, if we increase the CPU by an additional core, we might get 5 to 10% of computational power. However, with quantum computers, if we have a computer with like 100 qubits, if we increase it by an additional qubit, we might get double or triple the power. In terms of environment and error rate, classical computers can operate in the normal environment, and they have less or low error rate. They are not affected by the normal environment. While in quantum computing, the error rate level is high, and they are extremely sensitive to the environment. You will see that some of the quantum, in the next slide, that some of the quantum computers require a very severe condition to work, such as extremely cold environment, close to the absolute zero. In this slide, I will give you an overview about the most popular quantum computing types. As you may know, this industry is expanding on many different fields. It's basically a race between the high organizations or big organizations. So in this types, you will see the maturity level, you will see the companies, as well as the pros and cons for each type of these computers. Starting with the first type. The first type is called superconducting, which is the most mature technology type. And its qubits is based on the electrons. Many companies follow this track of development. As you know, electrons are the smallest units in particles. Therefore, this makes this type of computers extremely fast. However, it collapses very easily and very quickly. And they need an ultra-cold environment to operate. Companies here is like IBM, Google, Amazon, and Intel. The second type of quantum computers is called trapped ion, which is the second most mature quantum computing technology. Its qubit is based on ions. Ions are the largest particles, and therefore this kind of computers is very stable. However, it is very slow in the operations. One of the companies that is adopting this kind of computers is called Quantinuum. The last type we have here in the list is called cold atoms. And this kind of computer is, or technology, is a promising technology. Companies that are following this kind of quantum computers is called Pascal, which is building their technology on this atom-based systems. Advantages is that this kind of computers can operate in the room temperature and it's extremely stable. However, it requires improvements in the laser scaling in the system. Next slide will show you a video about the third type of quantum computing, the cold atoms. As you can see, this is the size of the computer, and this is the building process of it. And here you can see the lasers, laser waves. Moving on to the last subject in today's session, which is the quantum computers in AI and ML era. First of all, is there any relationship between quantum computing and AI ML? Well, quantum computing in the era of AI ML works hand by hand. This is not a competition between AI and quantum computers, but it is rather a mixture between these two different technologies. Each one of them complements the other. Quantum machine learning is the intersection between quantum computing and AI that's expecting to change how the future looks like. Individually, quantum computers are amazing and AI is amazing, but combining them together might be unstoppable. So we can define the quantum machine learning as the field that aims to write quantum algorithms to perform machine learning tasks. Quantum machine learning is illustrated in 4 approaches as follows. The first approach is called quantum-assisted ML, which uses quantum computers to accelerate the training or the development of models for classical machine learning. Example of it is, for example, Siemens quantum-assisted reinforcement learning and data analytics speed-up model. The second approach is called quantum-enhanced machine learning, in which quantum computers could accelerate a particular computational subroutine in classical ML. Example of it is Airbus QML, which is used to model the performance of aircraft designs. The third approach is called ML-assisted quantum, where classical machine learning is used to optimize the compilation of quantum algorithms for different hardware platforms. Researchers in this approach are using ML to perform error correction for quantum computers, as robust error correction is required for practical quantum computing. The fourth approach we have here is called quantum machine learning, in which it is contained within the quantum context. So machine learning here will be necessary to make quantum computing scale, and it will be used to improve the quantum error correction measurements. So to summarize it, the first 2 approaches are using quantum computers to accelerate or enhance the existing machine learning models. The third one is using the classical machine learning models to optimize quantum computers. While the last one is using the AI ML within quantum computers, separated from the classical ML. By this, I conclude my presentation. And thank you all for listening. If you have any questions, we'll be happy to answer them, my colleagues.
So can we invite everybody to the
Yes, yes.
Okay.
This one.
So thank you very much, Engineer Abdulelah. And we would like to invite the two Engineer Abdullah Lisa and Engineer Abdullah Lisa. So if it is all right, I can be the moderator.
Of course.
So we thank you very much for the presentation. And we would like to ask you, is there anything else, any other domain that that you think that our students should be learning in the quantum computation field that has not been covered so far?
I'd like to start by congratulating everybody over here to stepping up into out of their comfort zone. It kept being said, and the comfort zone is your enemy. And everybody over here, I see they are aspiring to get into an area where they are challenging themselves. The domain that you're referring to, Dr. Naya, is definitely something that we intend to cover in our next session, which is in the cryptography area. I think my colleague Abdulelah will definitely cover it, inshallah, in the upcoming session. I don't want to steal his thunder, definitely. And it's a way for us to re-invite you again, inshallah, and we'll see more of it in the next session.
Thank you very much, Engineer. Do we have any questions from the audience? Yes.
There was the idea of superposition, right?
Sorry?
The idea of superposition.
The idea of superposition, yes.
In classical computing or radical computing science, we have a concept similar to that that's called non-determinism.
Non-determinism.
Yeah, so this means a computer is a machine that can coexist in more than one space. Not necessarily two, it could be infinite. So particularly when we talk about finite state machines, so in this, the concept is there that the machine can coexist in more than one state scanning at the same time. So is it a similar thing or is it different?
Yes, superposition, and maybe Abdullah could help me later on. The superposition state has been taken from the quantum mechanics, where you have, and this is proven practically, where the particles can have multiple states, but the moment you look at them, the moment you observe them, this is called the observer state. Sorry, the observer, they call it. The state will be collapsed right away. Okay, and the particle or the electrons will only choose one state. So without observing it, it has all possible states. Yeah.
Because usually non-determinism is considered more powerful yet imaginary compared to deterministic approaches. The deterministic approaches are more, the hardware can be built on that, they are more practical. While non-determinism is something more radical and it can do wonders, but in terms of implementation, there are again limitations over there. So maybe there is some catch between superposition and the non-determinism philosophy in classical computing.
The word that you mentioned, the imaginary, right? Classical computing normally works when you have the power for it. But quantum, as soon as you add, increase it by one, it does not double, it actually increase exponentially, where the classical one linearly. So every bit you add definitely adds a greater value instead of just adding single one. For example, the high computing super computers, we all have the power that we do parallel processing, and we could say it's an imaginary results because it does parallel processing. But in the quantum world is totally different because when you add, even though it's still an emerging technology, but as soon as we reach to that supremacy, to the level that we say quantum now has surpassed the classical computing, and we have the number of qubits that actually does a value to our application now and create the performance advantage. So I know and understand that what you are aiming for, and yes, it is an imaginary thinking, but all of the studies now and theoretical are coming to light and applied to on the hardware itself. So the qubits, the superposition, all these are all theories, but now they are applying it on the hardware appliances as well. So we will see a lot of news related to the hardware, the error correction, and so on in the next couple of years.
Thank you. May I also add something? The standard algorithms in quantum computation, Grover's algorithm, Shor's algorithm, BB84, they are all probabilistic algorithms.
I have one more question. That's about the quantum communication. So it is stated that it is actually detect the temper immediately. Temper detection.
Temper
Detection.
deduction.
Detection.
Yes. Detection, yes.
Yeah,
Yes.
during communication. So yeah, during communication, we can detect if some bit was tempered or some external factor has changed that bit, maybe due to channel impairment or whatever. Currently, we are also having certain algorithms that can detect, we call them as error detecting ports or error detecting mechanisms. However, they can also provide error correction capabilities as well. So rather than going for retransmission or avoiding transmission, so they are capable of correcting them at the receiver side. So is there anything related to that in the quantum communication as well? Are they only provide detection mechanism, not correction?
As Abdulelah, engineer Abdulelah mentioned, they will work hand in hand. So obviously there are work to be done on the quantum side, but classical computing, all of that applications, as you mentioned, there are new or AI applications or also algorithms that detect any tampers in the classical way. There are going to be quantum algorithms are detecting, but in the world of the quantum itself. So still, it's an emerging technology. Most of the advancements are focused now on the quantum computing. Quantum communication and quantum sensing will still be a next buzz thing, but the focus nowadays in the world is quantum computing. Quantum communication will also go to the space as well to send all of that information, but it's still an emerging technology. The word is emerging is very important here because everything could change. All the information that we know could change with one discovery.
Thank you. May I also add something? I also keep feeling like adding. So whatever you can do with a bit, you can do with a qubit. You can just ignore all the other possible states. So every single classical algorithm you can do with a qubit, it's just not worthwhile because it's extremely expensive. It's just not worthwhile. But what you can do additionally with a qubit is because whenever you look at it, it collapses. That's something you cannot mirror classically. So in classical cryptography, when Eve listens to a channel, you cannot know she listened. But in quantum computation, just looking, she doesn't have to touch, just reading. you can see that there was a presence there. So this is something that you cannot mirror in classical computation. Thank you very much.
So basically, the qubits actually have feelings. So it's easy, basically.
Thank you.
Yeah, just a minute, sorry. Just I prefer the idea of shifting it from a science approach into a practical approach. Onto your question, one of the companies that we've evaluated last year, they were proposing the concept of what Abdulelah had mentioned, the quantum key distribution. With it still, it's an emerging technology and it's a challenging area. However, we've seen where they basically install devices between two nodes, two data centers, digital assets that are trying to communicate. Onto the example of where Eve is actually listening to Bob and Alice. The moment a listener takes place, where we are all cybersecurity professionals over here, there is a threat that is called harvest now and decrypt later. With quantum computing coming in part, we are really afraid where it happens, and then your encrypted data will be decrypted. Onto this example, basically the channel of communication between the two nodes, they install another two devices between the two digital assets. If a listening takes place, it will generate a new key, and it will say, this is our new way of doing the method of communication. And with that, still, this technology comes with challenges. First of all is the distance. They're still trying to perfect it, but it's a matter of time, in my opinion, that a technology will be perfected one day or another. It started with 20 kilometers, and nowadays we've heard from the Chinese, they are doing it with an example of what Abdullah had referred to, onto the space. They've achieved around 1,000 kilometers. They're getting there. Another challenge is the cost itself. We are in need of a global mandate to a point. Now, I have a control of my own jurisdiction, but if I'm communicating with an external entity, I cannot really mandate them to install those devices they are referring to. And those devices are quite expensive in their nature. Inshallah, Abdulelah knows it better than I do. We are aiming to host those solutions in Aramco, inshallah. And if our time permits, we can definitely invite you over to see it in the Saudi accelerated innovation lab in Aramco and Midr Tower, inshallah, 13th floor. Thank you.
I think that would be an excellent opportunity for our students, because we talked about this transmission of over 100 kilometers that the Danes did just recently. So it would be excellent. Is it? Can we ask you which technology would you prefer?
It's not yet. If you are aiming to the vendor name by itself, it's still under the evaluation stage, and we are
with optical cables.
It is through optical cables.
Yes, it's basically using optical cables where photons are being sent between the two endpoints. And these photons are in superposition state. So when we say they are unbreakable, this means that any, let's say, man in the middle tries to observe the photons. Each photon is observed will be collapsed. So if I'm sending 10 photons, for example, to you, if the attacker was able to observe 3 of these photons, then they will be collapsed. The other side will receive the additional 7 photons. He will synchronize them with me, and they will be used to create the encryption keys. That's why it's theoretically, maybe and practically impossible to eavesdrop.
Just one thing that I observed. So this means the communication will be purely one-to-one. And what I conceived from your explanation that the communication that we are talking about is purely from D to device to device. So what about the shared?
Not broadcasting.
So it's not any shared. It's not meant for shared channels.
This technology, from its name, quantum key distribution,
Yeah.
to distribute the encryption keys initially. So both of us can share or can create the same encryption key securely. And after that, we can communicate by encrypting the data using this encryption key that has been created. through this
So as
process.
more devices will be used, so this means another, for example, N-1 connection will be established.
Yeah, later on, any connection, any number of connection can be established. But
not the shared
initially,
channel, not the shared channel phenomenon.
I think
The shared,
Shared channel, shared bandwidth, shared spectrum.
no, not the shared, because these are just keys to distribute to that. And then when the end recipient receives that, they will communicate using the shared channel with that key. So the
Okay.
private is private.
So key distribution would be private, and that's why aggregation can be.
so. This channel is not intended to transfer or send and receive information.
It's
To
meant
be
for
used
key
for
distribution only.
for key distribution.
And by shared, do you mean distributed so that you have more than 2 users?
Yes.
That's okay. So for that, the standard QKD that the technology that they have now is not yet ready, but there are algorithms based on multiple entanglements which would promise that. So they are in way lower stage of applicability. But the QKD that we hope that will be used soon is 1-to-1.
Thank you.
First of all, thank you so much for the very gentle presentation. As cybersecurity students, we have a question. What are the potential applications of what are the potential applications of quantum computing outside of cryptography? So, for example, in threat detection, vulnerability analysis, and so on, because there was a lot of heavy emphasis on cryptography. We're interested to know what other areas of cybersecurity quantum computing has.
Thank you, Lorena. As of now, the 3 elements in cybersecurity are the quantum key distribution that we've recently spent some time on it. The second part is the QRNG, which is leveraging the quantum mechanics into developing RNG. It starts with RNG where you develop your own script, and then eventually this is not random number generator. It was then challenged that this is through a pseudocode. True RNG came in, and then QRNG. In fact, QRNG is utilized for instant messaging if you are to secure communication between 2 ends. And we've seen some applications in this approach. However, they are still coining it and trying to contain it with the East. The third one is the post-quantum cryptography. I hate to disappoint you, but it is actually in our area of cryptography. There are some studies that are being taking place, especially in our sister division within our department, to evaluate what if an adversary has his hands or her hands on a quantum device, what could happen to our classical defense. As of now, nothing has come to the surface, and it has been our mission to clear something, what we call it FUD, which is fear and doubt and uncertainty. This is where any emerging technology comes to the surface. A lot of vendors are trying just to sell you this sense of fear. And in a matter of fact, we've heard the Y2Q, which is a year to quantum, something very, they're referencing the Y2K back in the days when 2K came in. And this is where our colleagues are working together to just draw the line if this is an actual thing, it is really a reality, or this is actually a vendor attempt to trying to sell you fear.
Thank you so much. We talked about the Q-Day.
Also, if you remember from the presentation, I mentioned that the existing quantum computers haven't reached to a level where they can be better than classical computers, and they're also not posing any cybersecurity risk as of today. Maybe the only, I'll not say attack, but threat that we all of us must be aware of is the harvest now, decrypt later, or store now, decrypt later, where the attackers are storing the encrypted data, keep them aside until the quantum computers reach to a level where they can break the, let's say, RSA encryption. And after that, they can get the information if they're still valuable at that time.
I think this one. Thank you. Thanks to Mr. Abdulelah, and thanks for the stream analyst. You have mentioned in the slides that currently quantum computing still not to the level of classical computing. Still the classical, I believe, what I understood is outperform the quantum computing in the current state. But hopefully in the future, I mean, the expectation that the quantum, hopefully anyone have access to quantum will beat maybe a supercomputer. So that's I believe the ultimate aim of working with the quantum computing. So my question is there any stable version that can come close to the say optimal quantum computing, or at least that can beat the supercomputer up to now, or when expected to? Is there any company that have promised to have delivered this one near future? And the second question is regarding the maybe what's a question regarding the application of quantum. So if everyone have access to quantum, and if we shift to the quantum era, where the classical maybe will not be in use anymore, let's say we talk about maybe 10 years or more. So is there different than the same condition of classical? So now everyone using classical computer. So if we shift to the quantum era, maybe you can talk about the potential and also the threats that's also exists. And for the quantum, for the cybersecurity students, what the could maybe research directions for them to be well prepared for that future. Thank you.
I can start by answering the second question, then hand over the first question to my colleague Abdullah. In terms of the cybersecurity threats that are associated with quantum computing, first of all, the quantum computers will not replace the classical computers, because there are certain applications, certain use cases that are applicable for them, for the quantum computers, which are impossible to be solved by classical computers, or they can be solved after 1,000 years. And at the same time, there are a lot of use cases which are applicable to classical computer, and they will continue. Okay, because also classical computers are still evolving. Now, in terms of the threats that are posed by quantum computers into the classical computers, it's mainly related to the cryptography and one type of the encryption, which is the asymmetric encryption. Because there are two types of encryption, as you all know, the symmetric and the asymmetric. Cryptographers and scientists are saying that quantum computers ultimately may drop the security of the symmetric encryption by 50%, which is tolerated, which is okay. But they will ultimately break the widely used asymmetric encryption, such as the RSA, because RSA is depending on mathematical equations and factorizing a prime number. And this will be, maybe after 10 years or so, extremely easy for the quantum computers. And here is the true risk, the true threat of it. I hope I answered. Yes. Yeah.
Thank you, Engineer Abdullah. Thank you, Dr. Abdullah. The same question I asked to two people. One is a CEO of one of the companies, and the other is a professor in Oxford University. I asked them exactly the same question. When will it come? What will happen? What companies? He said, currently, everything will come. In the future, the quantum will reach to the expected level and everything. But now our focus is on the young generation, the young students, the talent. Those will actually take that true step and achieve the quantum in the future. So that's why, and I asked them, so why are you now advertising all of that quantum? He said, I'm gathering to build the new generation. His uncle also, by the way, won a Nobel Prize in quantum as well. So he knows all of what's going on around the quantum. So his focus is not on achieving a quantum qubit level or a power difference between classical and quantum. His achievement is to build the knowledge, spread the word, have a much knowledge people around in the room, especially in countries that don't have a quantum knowledge, especially in the Middle East as well. So his focus is gathering the people, spreading and educating, sponsoring them, helping them achieve. And those young talents, he said, what made the difference with error correction, guided us, even though we have PhDs, 100 PhDs, professors on quantum hardware, but with the new eyes of the young, help them different and navigate through the quantum itself, the hardware. So also I insisted in having an answer, like when will the quantum achieve that supremacy? He said always the quantum will work hand in hand with the classical, but what we are focused on is the knowledge. Every time I asked him that, he shifted all of the conversation to the knowledge, the people, the young, the talent, and the invention is always built from the young. Also, he reached out to me as well, saying that there are people, if you want to spend the knowledge with them, create network connection, also invite people to go to Italy and to go to UK to learn about how the quantum works as well. Even though, yes, I wanted to have the answer about the quantum, when is it going to reach? But the end result, he said, it will come with time. It will come with dedication, with people, and with knowledge as well. So I couldn't have that true answer that answers my questions there. So hopefully it's the same.
Yes, thanks. So you mentioned, you mentioned about quantum and AI. So it will be different than supercomputer and AI, or quantum and AI, or are they similar, are they different?
Before we get to it, Dr. Abdullah, and I'm just trying to get it back to your original question, when will this risk materialize? According to CISA, this is the Cybersecurity Advisory Arm in the US, they're saying it will take a decade and it could extend to that point. However, what Abdulelah had mentioned, is because of the nature of its exponential way of how it's advancing, it's a threat, and we are glad for all of us to make a call into an early stage to visualize and rather study the concept of quantum and what does it actually entail for the cybersecurity aspect. NIST, since 2016, they've announced an open source race for everybody to submit their algorithms. And in fact, they are putting an end to it with this year, where 2024. As of now, we're hearing some Kyber, Sphinx, and Lithium, and so on. Those are the algorithms that are proposed as candidates for quantum computers to be rather safe and be quantum resistant. The quantum technology still has its own challenges, and putting it into our practical world, one of the examples that Abdulelah had spoken about is for it to operate, it needs to be on absolute zero. For that, you need to really have extensive cooling for a processor to work. I think we've seen it all, where we have seen IBM's Mock, all of the spinning around, that's all of it. The process is very small. All of what we are seeing is an intent to keep it cool to an extent. Another example is the laser, where you have the sense of accuracy. Again, if I put it into our practical world where we actually work, every now and then a jet flies by, any simple resonation may trigger the error rate where the quantum needs to reset its capability. On to your question about quantum and AI, I think I'll pass it to one of my colleagues just to.
Actually, there is a mixture between quantum and the AI. They are working together. So sometimes you might see the classical AI models can be used to enhance the quantum computers' error rate and to make them to scale. Sometimes quantum computers could be used, their capabilities, their power could be used to accelerate the classical ML. And sometimes the quantum computing could use its own AI to also, because one of the most important or most, let's say, problem with the quantum computer is the error rate, and instability. So maybe one of these models or properties of AI is the using machine learning and artificial intelligence models with the quantum computing to resolve these issues.
Okay, I have another question. I was under the impression that quantum computing would overtake the classical. So it's very interesting to see that there's a debate between which one to use. So can you give us an example of when you will use a problem that would be better solved with a classical computer and one that would be better solved with a computer?
Talk about the applications of quantum.
If you want to open your laptop, if you want to open a Word and save it, and you're not going to run it on a quantum computer. That's exactly the same. If you have a formula that runs on a supercomputer for 2 weeks, for example, if you run a formula that has that you want to results, you want the results in 5 days, but because of the capability of the supercomputer, it cannot give you the result until 10 days, so you lose the value of that result. So you need the value, the results in the 5 days to take a decision. For example, one example is if you want to take the reaction of a big, let's say, oil reservoir, and you don't want it to explode. So what's the limit exactly to the bit of seconds when before it exploded and the valve opens for the pressure to go out. So when you apply this formula on a classical computing, you're not going to have the result in time. The container will explode. So in quantum, you probably can have that result and exactly know when is the pressure is going to go out and operate normally. So basically, it's these situations.
But that's a very sensitive thing. I want something but there's a lot to talk of a lot of errors. So how can you trust that it's the correct thing?
That's why when we started the discussion, we said it's an emerging technology. It did not reach to a level when we say it's 100% valid. It's going to be 100% giving the right results at the end. So it's an emerging technology. Still did not reach to a level that we trust and to give our production information in it to give us the results. So it's a testing phase, testing how it's react and the outcome of the formula, how will it give us. So I'm just giving you an extreme example. We could just test it on a simple matters like when we wanted to build a car that runs with the air dynamic. So we want to design the car when the air is not facing the car, but it's helping it go faster. So using the quantum, we could use that. Even though it's not time sensitive, we could do it in classical, but sometimes the classical cannot bend to a level that these algorithms actually give a result that you want. So there are multiple use cases can be applied. Yes.
Due to the nature of quantum computers, many are pushing variational quantum algorithms. My question is, when will there be no need for variational quantum algorithms, and just it would be easy to use just Shor's algorithm or pure quantum algorithms? So what is the future of error mitigation in quantum computers?
Normally, as mentioned earlier, it's an emerging technology and everything is changing. And every institute or a company trying to create their own algorithms and trying to advertise it and try to mix the AI with it. So even though engineer Abdulelah mentioned there are 4 types of AI helping quantum helping AI, but in the future probably there will be more in those targets, probably 5th and 6th also types. And at the end, all of the quantum community wants one united algorithm and one standards and all of that is not yet available. So all of the standards, policies, ethics around the quantum, it's not yet solid and clear. So still ongoing process, all of that.
Just to add to what my colleague mentioned, bigger companies such as IBM were focusing on developing quantum computers with a higher number of qubits. For example, the first generation comes with, let's say, 200 qubits, second generation 500, third generation with 1000 qubits. But the problem was with the error rate. So you might lose like 300 qubits or so because of the error rate and instability. But recently, IBM started thinking of developing new quantum computers, considering reducing the error rate. So not only thinking of increasing the number of qubits. So I think maybe 2 or 3 months ago, they announced a computer with like 100 qubits or 200 qubits. I think I've read 100, maybe I'm 127, yes, with a lower error rate compared to their previous generation.
Presentation and great discussion. Talking about the collaboration between the quantum research and AI research, can you discuss any recent ongoing research efforts in enhancing the quantum computing and addressing specific challenges in AI? So, for example, I heard about the concept of quantum generative models, which aim to generate realistic data for training AI systems. Can you actually some insights about it?
Normally AI use cases or companies, they don't reveal most of their work. They want to patent it. They want to dig into how they benefit from all of that approaches. So most of when we searched, we gathered, we asked, the companies are not sharing that information, especially in the algorithms. They have opened systems, platforms for us to test, to apply our algorithms, but normally they because the algorithms sometimes are owned by their own creators, they don't want to share it because it's still not did not show of great value, but they know that in the future this will help them if the qubits reached, for example, to a 2000 or 3000 qubits. When they apply that algorithm at that time, it will give a greater value. But now it's hard to get a result from these algorithms that they are building.
Just to give an example onto your question is one of the companies that we've evaluated in the Far East last year, what Abdullah had mentioned, whenever an algorithm is proposed, if it's an open source for us to tap into it, that's a good sign. If they tend to have this mechanism of having it as a block box, that's for us a red flag. One of the companies, they've illustrated this for in front of our executive management. They have broken an RSA key in front of us. And it actually happened. All it took Abdulelah to go back and then generate a new key. And we told them, go ahead and just break it. You have 2 weeks to do so. They did not break it and they did not come to us. A lot of companies and vendors are tapping into the FUD, which is a fear, uncertainty, and doubt. A lot of people are just tapping into it just to get your attention. And I'm glad that we are exploring this venue. This is an emerging technology, as everybody had mentioned. And allegedly, these are mere claims. As of now, nothing has been broken, not even RSA that is susceptible from an asymmetrical approach.
Thank you so much, Engineer. I think that is very useful what we learned from you. I would like also to add to what one of the students says, and I think it latches on to what you said before. So quantum algorithms are probabilistic algorithms. They're not deterministic, they are probabilistic. So if you have a very good probability, 99.99, you're happy with that one. I would like to also add that we are talking about parallelism. The problem in quantum computation is the measurement, because when you measure, you lose the parallelism and you are left with one solution. And that is why the question is so hard to design quantum algorithms that are actually useful for us, because they have to be problems and solutions that start with a large search space, but you're happy to, in the end, have one. And that is why Grover's algorithm is probably the most successful algorithm. Right now in 2024, there was announced a competition by ACM, I think, who can find algorithms, and I'm now talking theoretical algorithms, that actually could be useful and show theoretically better results than the classical ones. And I'm just saying now for the academia audience, NP-complete problems are not shown to benefit from quantum computers other than normal parallelism, right? So that's what I wanted to put into, just to give this side of the story. Thank you. Yes.
So I'm doing research, and one of our research criteria is that project that happened in KSA. So one of them is collaboration with a foreign company, and their focus now is in oil industry, which is, I believe, your company, Saudi Aramco, focus on oil in that section. So they are searching on, increased efficiency on extraction, processing, and distribution oil, especially in airflow in aircraft. So do you have an idea of how this process, so I can support my research? I know this is a very tricky question, but if you don't have answer,
And I honestly haven't heard about it, but just to get everybody's to the same boat. Aramco has about 80,000 employees, and our department is one of 400 other departments. So it is vague to us as much as you.
Any more question?
Yeah, besides investments, what has been Aramco's work with quantum computers? So what have you been doing exactly, if that makes sense?
To answer your question from the cybersecurity angle before I pass it to my colleague Abdullah, Beside investment is one of the major angles because it's an emerging technology, something wide, as they would describe it. We have the Aramco's venture. This is the arm for investment, and they are basically telling us if you see anything that is promising to your extent, go ahead and invest. And there are some investments that took place, but I don't think this is the venue for us to speak about. However, from a cybersecurity angle, as I had spoken or rather highlighted earlier, the QRNG is an area of interest for us to evaluate and tackle, which is securing the communication through instant messaging and still ongoing from our end. The quantum key distribution, which I'm sure Abdulelah will cover it more in his next stage. And the third element, which is the post-quantum cryptography. Everybody is pretty much waiting for it to end by list race for this year, inshallah.
Anything that I'm gonna say is all available in public news. So, as mentioned by my colleague Abdullah, and Aramco is investing in the new technologies and trying to find the best way to invest these technologies to help in the energy section. So, one of the companies is a French company that Aramco invested in. It's a startup company that builds their quantum computing on a cold atom or neutral atoms. Yes. So it's still an emerging technology, trying to expand in their computing capabilities. And their focus normally is on AI and financial sectors and more into the computing enhancement stuff related to energy, related to financial, as I mentioned, and AI in general from there. Also, it's available in public. You could just Google it and you could see all of their investment advancement in that field. So we're also researching as well. We're into this new field. Still, it's an emerging technology. No one has the upper advantage. It's a race for all of the companies or universities. We wanted to reach to a ground that we are confident that the quantum is knowledge. The knowledge of the quantum is now in our capability, and we could actually build algorithms, build applications based on the algorithms that could benefit us and enhance the way that we also do the business in company Aramco or other companies. So as mentioned, other universities are investing in their students, collaborating with other companies, either if it's in the Far East or in the US or Europe. All of them are investing on the knowledge, the discovery, the experiment, all of that. Nothing is not gave results to give an advantage, but now all of that is just investments, discovery, knowledge, and experience. All of that currently.
If you allow me, I have a question, probably could be a general question. What's the regarding to the quantum computing? What's the disadvantages for that technology? That you discovered during the investment, and what's the future for using the quantum computing technology for to apply, especially for robots, controlling the manufacturers, while it's new technology, faster, as you said, it will accelerate the processing, taking actions in the health sector to do surgery online and etc. So, in discovering the issues, so can you say divide my question for two parts? The disadvantages that you discovered and you wish that to be solved, and what's the future for it in different sectors, in drug manufacturers or health, like health?
Different, great questions. The disadvantage, what we saw that each company has its own algorithm, its own hardware, its own language. Let's say its own language. So when we try to, let's say, build a case, understand how would we apply that case into, let's say, company or quantum company A, when we move to quantum company B, it's going to be different because that behavior for the quantum is going to be different. The qubits behave different. The application will give a different results because of the qubits. Let's say company A is electrons. The electrons move fast, but they need the power to the energy to be kept cool. And when we apply it on when we apply the same algorithms on applications or on quantum cold atoms, is totally different behavior, or it requires some changes. So our disadvantage, what we saw in general, not a specific company, is the algorithm applying it to the language. Let's say the language, when we speak to the quantum, it's going to be different. So we need to understand each algorithms when we want to talk to a quantum computer. And this is the disadvantage that we saw, because every time we need to teach an employee or a student, they need to understand that language. I think you experienced it with IBM. So when we shift, you want to shift your students to another platform, you will see that disadvantage right away.
But theoretically, aren't the circuits all the same? Because they all rely on the same gates.
Yes, that's a different behavior inside the quantum computer, but we need to build the layers of the applications first, and then because the language does not understand.
Do you mean by language? So, for example, with IBM,
Yes, exactly.
Yeah. Okay.
Exactly. So when we build the application through Qiskit, it's going to be different totally when we apply it to.
So you're not talking about open chasm, right?
No. So this is what we noticed as a disadvantage when we saw the quant. But for example, and we compared with classical computing, the language is the same. We could apply it all computers. If it's a Dell, if it's a Sony, if it's whatever, it's going to be running. So that's what we noticed. But now the good thing that AI and machine learning will work hand in hand to come and combine all of that under one platform, an umbrella. And probably one of you could join that in the future and actually build this capability. Probably a company that you could lead or be a CEO of building this capability. So it's, yes, a disadvantage for the companies, but an opportunity for you as an individual.
So, thank you for answering the question. This could lead for another question. Expanding the technology in the future, it could be difficult to be expanded. I think, especially because we have, as you said, to apply it, we had to, let me say, reprogram the qubit to suit the new, even the new field. Even so, for the manufacturers in the same field, but they are different. Let me say, different. They are using different algorithms. As you said, to expand the technology, we can say the growth for that project could be very slow.
Normally, each company will focus on its own, and any breakthrough in any of the companies will help the others. For example, finding an error correction or a certain algorithm will help the others. So any advantage in one of them will be advantage for all of them. So it's not just a solo. Yes, it's a race, but it all will complement each other. They will help each other.
I would also like to add here, in the beginning when classical computers emerged, every company had its own assembly language. And translating an assembly program from one company to another was not done automatically. We are living in the same era now with quantum computers, that every company develops its own language. And it is the equivalent of an assembly language of talking to the quantum computer, because it is at the level of the gates. as we do with Kisi. So there is no standardization yet and no automatic translation.
Yeah, I think you just mentioned it. The big companies need to come to sit together and come to a standardization in terms of the development of the quantum computers. But I want to get back just a little bit to the disadvantages of the quantum computers. I'm not sure, maybe it could be as a disadvantage or a negative side, let's say dark side of the quantum computers on cybersecurity. As we mentioned earlier, they could break the widely used asymmetric encryption, the RSA. So this could be one of the problems or side effects of having quantum computers. That's why cryptographers are now working on different technologies, which my colleague Abdullah mentioned, the quantum random number generator, the quantum key distribution, as well as the post-quantum cryptography algorithms.
May I ask you a question related for the physical things? Have you noticed any things related to the heating temperature while you are using the Q bit instead of using the bit side?
Well, we haven't been exposed physically to the quantum itself, when we compare it to the classical computing, we have our data centers in the company, and the cooling is massive, huge, massive kilowatts, exactly. And when you go in,
slow to transfer, right?
Yes.
From 0 to 1. First.
Yeah. So the fans, the cooling system is so huge. So when you go inside, even though one of the advantage of the quantum will be that it will use less power to run the quantum computer. So one example, they mentioned that one of the neutral atom company, they said you will run this big quantum computing on a power exactly the same as a hair dryer. So exactly the same power that you use on a hair dryer, you will use the same amount of power to run this quantum computer, this big quantum computer, comparing to the super computers, which has coolers like this room, big of a size, and imagine the electricity that will use to run all of this machine. So it's an advantage on the power itself.
Beside the standardization point, where it is a pain area for us, the sense of unification, to have all quantum computing talking the same language as we can speak. They have realized that due to the errors, is it because of your geographical location, the environment surrounding you, or even the financial costs associated with you trying to cool up any quantum computer in a sense? They are already talking about QAS, quantum as a service, which is somewhere in the cloud where you can submit your transactions and have any sort of return. Yet again, it's an emerging area where people are just exploring how can we perfect it in the download.
So most of the future will be for cloud services.
It could be. And for example, we've seen it in cloud, especially in North Scandinavia, where it is really cold for them. They don't really spend an amount or rather an effort to cool up your processing units.
Engineers, I would like to take this opportunity again to thank you very much for coming here and sharing your knowledge with so much heart and with so much willingness to share. So let us give our guests a big clap. We hope to see you again next week. And we hope that you and your group can also benefit from our students according to your needs. Thank you very much.